So last week we started with a new module which is what transient analysis, right? So time domain analysis of RLC circuits, right? So what we saw there, we saw that the equations, there was a switch. So we had three steps just before switching, that is t equal to 0 minus, then just after switching, that is t equal to 0 plus, and some time after switching, that is t greater than 0, right? So we divided each problem into these three steps, right? And while solving those problems, what we came across, we came across special type of equations which are called as what? Differential equations, right? So they were of the form di by dt plus p equal to q pi, right? So how we solve this? We said it is nothing but I into integrating factor equal to integral of integrating factor into q plus c, where integrating factor is e raised to integral of p dt. The variable is dt, right? So this is how we solve this, right? So what is the problem here? The problem is that we need to solve differential equations. This is not an issue for a single degree, but we might have equation of degree 2, right? And we had only one inductor and one capacitor in all the circuits, right? So as the number of order of the differential equation increases, the complexity will increase. So again, this method is quite complicated for complicated circuits, right? So what we do is we go to the next topic to solve this problem, which is frequency domain analysis of RLC circuits. Okay, so let's see how to do that. So what is frequency domain? Means d by dt, we are in time domain. So from frequency time domain, we have to go to frequency domain. So you have already studied this actually, but you don't see directly f, you see something called as s. So what is the topic where you have studied s domain? So that is nothing but Laplace domain, right? So this frequency domain is nothing but Laplace transform topic. So we'll use Laplace transforms to solve this, right? So let's start with the definition of Laplace transform. So what is the definition of Laplace transform? So in mathematics you have already studied this. So today I'll just give you an overview of this. Then actual problems will on actual electrical domain will go to from tomorrow, right? So if there is a function f of t, I want to find its Laplace transform. So we denote it as Laplace transform of f of t is given as f of s. Remember, this f is small, but when I in Laplace domain I make that f capital, and this t is small and s is also small. So how to get f of s? So that is f of s equal to integral 0 to infinity f of t e raised to minus st dt. So this is the definition of Laplace transform. So you might say, sir, we have studied minus infinity to plus infinity. Practically, what will be the time? It will be from 0 to infinity only. So we will be solving this in practical circuits, which are actually used in real time. So that's why it is 0 to infinity, where s equal to sigma plus j omega. Okay. Then there are conditions when this transform will exist, etc. So, and the inverse Laplace transform definition, that is not required from exam point of view, so I will not go there. So then there are some standard Laplace transforms, right? So we'll see that. So then Laplace transform of a constant k, what is it? Let's say this k equal to 1. What is Laplace transform of 1? You have studied this in mathematics. So it is what? Laplace transform of 1 by s. So for Laplace transform of k, it is nothing but k by s is the Laplace transform. So next we have Laplace transform of t raised to n. So you can always prove this, substitute this t raised to n in f of t, solve this integral, you will get the answer. So I am not doing that. So Laplace transform of t raised to n, you can prove it to be n factorial upon s raised to n plus 1. So if n equal to 2, usually we will get t square term. That's why I am showing this. So Laplace transform of t square will be what? 2 factorial is what? 2 only. So 2 upon s cube n plus 1, right? What will be Laplace transform of t? That will anyways come further, so I will not show it. So then third, we have unit step function. So what is u of t? u of t is 1 for t greater than 0 and 0 for t less than 0. So if you draw it, how does it look like? This is t and this is 1, right? So this is my u of t, this is my origin. So what will be Laplace transform of u of t? So if you solve this, so you'll get it as 1 by s. Okay, so then you have delayed unit step function, so it is nothing but u of t minus a. So u of t minus a, it is 1 for what now? T greater than a, and it is 0 for t less than a. So how will it look like? This will be t, this will be u of t minus a, this is 0, so it will start at t equal to a. So this is t equal to a, so here it is 0. So this is nothing but shifted version of u of t, so that's why delayed unit step function. So Laplace transform of u of t minus a, it is equal to e raised to minus as upon s. So in fact we will see that if anything is shifted or delayed by a, we multiply by e raised to minus as, rest all is same. So then fifth we have ramp function. So it is what? R of t. So it is what? T for t greater than 0 and 0 for t less than 0, right? So if you find the Laplace transform, it is Laplace transform of R of t equal to 1 upon h square. So that is what you can prove it in t raised to n also, where n is 1. So then similarly you have Laplace transform of delayed ramp function. So what it will be, as I said, you just have to multiply by e raised to minus s. So multiply this by e raised to minus s, you will get the answer. So then we have unit impulse function. So that Laplace transform, Fourier transform, etc. are usually 1 for it. So I'll directly write it. It is what? A huge amount of signal is generated for very small amount of time, ideally in 0 seconds. That Laplace transform is 1. Then we have Laplace transform of exponential function e raised to at. So it is given as 1 upon s minus a. So if it is plus, we write minus, and if it is minus, we write plus. So accordingly I have written, if it is minus we have plus, if it is plus we have minus. Okay, then we have Laplace transform of sine function. So sine of omega t, it is given as omega upon s square plus omega square. Then we have Laplace transform of cos of omega t, given as s upon s square plus omega square. Then finally last two we have hyperbolic sine function. So Laplace transform of sine hyperbolic of t. So it is given as same but with a minus sign, s square minus omega square. So you can guess what will be for cos hyperbolic. So Laplace transform of cos hyperbolic of t, what it will be? S upon s square minus omega square. So these are the standard Laplace transforms. Okay. So then we have some properties of Laplace transform. So properties of Laplace transform. Okay. So first is linearity property. I will not go there. I will go there only through which those are important from exam point of view. So first, from exam point of view, important is time scaling. So if Laplace transform of f of t equal to f of s, then Laplace transform of f of at is given by 1 upon a f of s by a. Okay. So this is the time scaling property. If you have a Laplace transform of f of t as f of s, so what you do, if it is at, means t is replaced by at, what you do, you replace s by a. So where a is from here, right? And you divide the whole answer by a. That is what is the meaning. So then we have frequency shifting. So frequency shifting. Okay, so it is given as Laplace transform of e raised to minus at into f of t equal to f of s plus a. Okay, so let's say my f of t is sine omega t. So I'll give you an example. So e raised to minus at sine omega t. Okay, so what was Laplace transform of sine omega t? It is omega upon a square plus omega square. So what is this? This answer is f of s, right? So what does this say? Replace s by s plus a. So where is s? So this will be s plus a the whole square, right? So this will be omega upon s plus a the whole square plus omega square. Okay. Similarly, you can do for cos and hyperbolic functions, right? So next, similar to time, frequency shifting, we have time shifting. Okay. So again, if Laplace transform of f of t is f of s, I am not writing that. Then Laplace transform of f of t minus a is what? E raised to minus s f of s. As I said, whenever it is delayed, it is e raised to minus as multiply. If this is plus again, this will be plus a. Okay. So this is time shifting. So next, is multiplication by t. So multiplication by t. So obviously it is what? Laplace transform of t into f of t. So it is minus d by ds f of s. I am going through it fast because we have already done this, right? You have also proved it in mathematics, but again I am repeating, you don't, the proof won't be as, you will be given a network and you will have to solve. So don't do the proofs for this, because the proofs are given in the books. So you may think that they'll come in the exam, but they won't come in the exam. So then we have multiplication by t. So then we have division by t. So Laplace transform of what it will be? F of t by t. So if you take the Laplace transform, solve using definition, you will find that it is integral s to infinity f of s ds. So this is not that important. So then we have Laplace transform of derivative. So write this neatly because this is very important. So if Laplace transform of f of t equal to f of s, then Laplace transform of f dash of t. What does this indicate? First derivative of t. It is given as s into f of s minus f of 0. So see this, very important. Small s into capital F of s minus f of 0 means you will substitute this in the time domain. Here you will substitute in frequency domain. And if I have double derivative, means taking derivative 2 times, then it becomes s square f of s, this is 2, minus s f of 0 minus f dash of 0. So again this is capital F, so frequency domain, this is for time domain thing. And this is derivative of time domain, you take f of t, then you substitute t equal to 0. Okay. So in general what we can say? Laplace transform of f n of t, where n indicates the number of dashes. So it will be s raised to n f of s minus s raised to n minus 1 f of 0 minus s raised to n minus 2 f dash 0 dot dot minus f of n minus 1 of 0, right? So if there are 2 dashes here, there is 1 dash here. So if there are n dashes here, there should be n minus 1 dashes here. So that's how you can generalize it, right? So next, Laplace transform of, similarly to derivative will obviously have integral property. So Laplace transform of integral 0 to t f of t dt, it is f of s by s. So this is the standard property. Then last two we have initial value theorem. So limit of, since this is initial value, we have t tends to 0. This way you can remember. Limit of t tends to 0, f of t equal to, it becomes limit s tends to infinity. Means if time is in 0, frequency goes to infinity. S into f of s. So next we have final value theorem. So it is given as limit of t tends to infinity. Since this is final value, so t tends to infinity. F of t, then limit s tends to this becomes infinity only. Remember, this does not go to 0. S f of s. Okay. Sorry, this is s tends to 0, right? So when 0 is here in time domain, it becomes infinity in frequency domain. When it is infinity in time domain, it becomes 0 in frequency domain, right? And it is always multiplied by s into f of s. Okay. So then you might require inverse Laplace transforms, right? So let's take some simple examples how to solve. So let's say I have find inverse Laplace transform of s square minus 3s plus 4 upon s cube, right? So this is my f of s. So therefore f of s equal to, how can I write this as, what you check first, you check whether the degree of numerator is less than the degree of denominator or no. If it is less, you can use it directly, right? So if it is less, right, so what I can do, I can write this as, I can separate the denominator. So it is 1 by s minus 3 by s square plus 4 by s cube, right? So if you want, there are two methods. You can use this method or you can use partial fraction expansion, right? But this method is simpler here, so I'll use this one. So in some cases it may not be possible to write it in this way. So what you will have to do is, you will have to use partial fraction expansion only, right? So I have to find inverse Laplace, right? So this will be, if so, what will write, taking inverse Laplace transform. So this will become what, f of t. So what is this? Laplace transform of 1. Inverse Laplace of 1 by s is 1. So what is 1 by s square? Inverse Laplace transform is t. So this will become 3t plus 4, 1 by s cube. So we saw that for t square it is 2 by s cube. So I can write this as 2 into 2 by s cube. So 2t square, right? So this is how we can find the inverse Laplace transform. So let's take one more example. So let's say f of s equal to 3s plus 4 upon s square plus 9, right? So you can write this. So you know that this is of the form s square plus 3 square. We just now saw that Laplace transform of sin omega t in the denominator as s square plus omega square, on cos omega t as s square plus omega square also. So probably you can write this as cos and sin terms. So if I separate this, I'll get 3s upon s square plus 9 and 4 upon s square plus 9. Means I can write this in terms of sin and cos omega t. So where omega is what here? 3 probably. So omega is 3, right? So first separate it. So I'll get 3s upon s square plus 9 plus 4 upon s square plus 9, right? So what is this? 3 into s upon s square plus 3 square. So s upon s square plus 3 square. So it is cos of 3t. So 3, so inverse Laplace will be 3 cos of 3t plus, what will this be? For this we require 3 upon s square plus 3 square. So I'll divide and multiply by 3. So this will become 4 by 3 into sine of 3t, right? So this is my f of t. I am taking inverse Laplace transform, right? So next is, you may have to do some manipulation. So if I have 2s plus 2 upon s square plus 2s plus 10, what you can do? This is not of the form s square plus 9, where you can write s square plus 3 square, right? But what you know, this is 9, 9 plus 1 means 3 square plus 1. So, right, or something like that. So you can probably square this, right? So this is called as method of perfecting a square. So what I'll do is I'll write here 2s plus 2. Okay, then you take the number as the coefficient of s. What is it? 2. You divide it by 2. So that will give you a perfect square. So that is what 2 divided by 2 is 1. So you write s plus 1. Then you square it. So what you get? S square plus 2s. Right? So you are getting the same number. Because how we can do this? Because a plus b the whole square is a square plus 2ab plus b square. So that's why we are dividing by 2 and writing that number here. So you are again getting a square plus 2s plus 1. So 9 is remaining. So I write this as plus 9. Right? So now what is it of the form? So I can write this as 2s upon s plus 1 the whole square plus 3 square plus 2 upon s plus 1 the whole square plus 3 square. So this is again of the form of cos omega t and sin omega t, but shifted versions. So if I have s plus 1, so what we saw, we have that property, right? Is that page? Yeah. I have, if I take the second term, it is of the form omega upon s plus a the whole square plus omega square, where omega is 2, a is 1. So what will this become? Omega is, here it is 3 square, so omega is 3, sorry. So this should be multiplied by 3. So to make it correct, I'll divide by 3 also. So what will I get? 2 by 3 into 3, and it will be what? E raised to minus 80. So e raised to minus t sin omega t. So omega is 3. So 3t. Right? So similarly, this will be s upon s plus a. So 2 into e raised to minus t. A is again 1. So e raised to minus t cos of 3t. Right? So this is my f of t. So this is one way to solve. But is this correct? That is the question. So if you see, this is for sin omega t. So let's say I write for Laplace transform of e raised to minus 80 cos omega t. So what it will be? It is what? Laplace transform of cos omega t क्या है? It is s upon s square plus omega square. So what you do for e raised to minus 80? S is replaced by s plus c. So it will be s plus a upon s square plus omega square. Right? So here I should have s plus 1, 2 times s plus 1. Right? So I can't use this. This is correct. But I can't use this part. Right? So what you can do? You can see this here s is 2 is common. So this can be written as 2 times s plus 1 upon s plus 1 the whole square plus 3 square. Right? So you have s plus a upon s plus a the whole square plus omega square as this s plus a upon, s plus a the whole square plus omega square, right? So you can write this as 2 into a is 1. So e raised to minus 80 will be e raised to minus t cos omega t. Omega is 3. So this is the answer. Okay. So I did this to give you an example of e raised to minus 80 sin 3t के लिए what we do. Okay. So let's take one more sum. So if I have f of s is 3s plus 7 upon s square minus 2s minus 3. Okay. So again, what to do? This you can't do anything. So what to do? You use method of perfecting a square. So divide by 2. So what will get 1? So since this is minus, we will use s minus 1 the whole square. So s square minus 2s plus 1. Right? But I want minus 3 here. So what will I do? I will use minus 4. So plus 1 minus 4 is minus 3. Right? So I am getting s minus a the whole square minus 2 square 4. Right? But here there is s minus 1. So in the numerator also I should have s minus 1 because this is the addition. So I'll write 3 times, I'll keep it s minus 1. So what will I get? 3s as it is minus 3. So I'll have to add 10. Right? So I'll get 3 times s minus 1 upon s minus 1 the whole square minus, I'll write 2 square plus 10 upon s minus 1 the whole square minus 2 square. So again this is a standard form, right? So it will be what? And it is delayed. So I'll use, and it is minus 1. So plus t now. In the previous time it was plus 1. So we use minus t. This is minus 1. So plus t. So 3 e raised to t cos hyperbolic omega is 2. So 2t plus 5 e raised to t. And this will be what? Sine hyperbolic 2t. So this is the way you have to solve this. Okay. So next I'll take one more example, but we'll use partial fraction expansion now. Okay. So I'm assuming you know how to use partial fractions. Okay. So I'll just take a simple example and then we can stop. So s plus 2 upon s times s plus 1 into s plus 3 is, let's say, f of s. So how we can do? So you can't use the methods which you used previously. So the only recourse is what? To use partial fraction expansion. So what we will say, therefore f of s using partial fraction expansion, this is equal to a upon s plus b upon s plus 1 plus c upon s plus 2. Right? Sorry, this is what? 3. Then what do? You cross multiply, you take the LCM, cross multiply, etc. Right? But what you can do is you can use a shortcut here. Since this is a linear thing, you can use a equal to what? This thing, substitute s equal to 0 everywhere except in this case, because if you substitute 0 here, what will get? Infinity, right? So you substitute s equal to 0 everywhere here, so what will get? 2 upon s is as it is. So s plus 1, this will be 1 and this will be 3 because s is 0, right? So you don't write the s also. Okay, so what will get? A as 2 by 3, right? So that is the value of a. Very simple. You can use this in the exam also. So then b, what is the denominator? S plus 1, equate it to 0. So s is what? Minus 1. Substitute minus 1 here everywhere. Again skip s plus 1. So it will get b equal to, so s is minus 1. So this will be 1 upon minus 1 into 2. So this is what? Minus 1 by 2. So that is b. Then what is c? S is minus 3. So minus 1 upon minus 3 into minus 2. So it is minus 1 by 3. Sorry, minus 1 by 6. 3 to the 6. Right? So what is therefore f of s? So therefore f of s equal to 2 by 3s minus 1 by 2 times s plus 1 minus 1 by 6 times s plus 3. Right? So then taking inverse Laplace transform of both sides, what will you get? F of t equal to 2 by 3s ka inverse Laplace transform will be what? 2 by 3 only, because Laplace transform of 1 is 1 by s. Then minus half is constant, so take it outside. Inverse Laplace of s plus 1 is what? E raised to minus t, where a is 1. Laplace transform of e raised to minus at is 1 upon s plus a. Then similarly this here, same thing, but a is 3. So this will be minus 1 by 6 e raised to minus 3t. Right? So this is the way we solve for partial fraction expansion. Then you have those types of partial fraction expansion. So you already know them. You have studied in mathematics. Okay. So we'll continue in the next lecture.